Today's lesson is section 6.5. It's called Use Proportionality Theorems. So we are going to have some theorems that allow us to set up proportions that will create similar shapes or similar items. All right, we have here, our first one is called the Triangle Proportionality Theorem, and then we have the converse of that theorem. So this first theorem says, if a line is parallel to one side of a triangle, let me back up. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So basically what you're looking at here is I have a set of parallel lines. Okay, so it's saying if you have this set of parallel lines, or the language of the theorem says if you have one line parallel to one side of a triangle, then it's going to intersect each side of the triangle and split it proportionally. And so what that means is if we look at this proportion right here, and let me color code a little bit. So it's saying that if we put RT in a ratio with TQ, okay, so that's this ratio right here. So if we put those two in a proportion, or in a ratio, it's proportional to the other side split. It's proportional to RU over US, okay? So do you see how the very top of this, RT and RU, correspond on each side? Okay, so that is referring to this side and this side. So do you see how those are both in the numerator? The other sides are both in the denominator. Okay, and so we're able to do this because the parallel lines break it proportionally. The converse is just the opposite. It says that if you have a line, so remember the opposite of this would be we don't know they're parallel. If a line divides two sides of a triangle proportionally, then it is parallel to the third side. Okay, so what it's saying here is, let's say we just did 4, 2, and we made this 6 and 3. And so what I'm trying to show you is if we've got, these, one is double of the other, then I know it's parallel. So then I would check this ratio right here. I would say, is 4 over 6 equivalent to 2/3? And so when you see that it is equivalent to 2/3, then we can say, oh yeah, these lines are parallel. Okay, so I guess this would be another theorem to show parallel lines within a triangle, kind of like we had all those converses a while ago. All right, let's put this into action in this first example. Find the length of a segment. So in the diagram, BE is parallel to CD. Okay, so I see that. I'm just going to reinforce that by just drawing over it. AB is 8, and so that's already labeled. BC is 12, that's already labeled. ED is 9. What is the length of AE? All right, so I'm going to just start from the very top here. I'm going to utilize this triangle proportionality theorem. Okay, and so let me start by writing out really the names of the segments. So I know that if I can put segment AB into a ratio with BC, okay, and so I took this side right here, all right? So I'm going to take those two and set that equal to the other side, AE over ED, okay? So see the pattern there. AB and AE are the two ones near the top. BC and ED are the two other sides. Okay, so then I've got AB, let's plug our numbers in, 8 over BC, which is 12, equals AE, let's just call that X. Okay, we'll call that X over 9. So I'm just going to cross multiply and solve. Now I can reduce 8/12 down if I want to. Okay, otherwise I'm just going to, cross multiply. So that will give me 12X equals, so 8 times 9 is 72. Divide both sides by 12. I get 6. So what is the length of AE? And so since I marked AE with X, that just means AE is 6 units. So AE equals 6. Okay. All right. That's one way to set this up. Now you can use other methods, especially with these smaller numbers here. So what I'm trying to really figure out is, what's the relationship factor-wise between these two numbers? Okay, so if I can see a clear relationship, then I could have applied that numerical relationship from 9 back to x. Okay, and so it just kind of depends on, what kind of grasp you have on how things are set up here. Okay, number 2, determine whether the line segments are parallel. In the diagram, segment PQ divides segment LM and MN. Oh, let me back up. Let me draw over this. PQ right here divides segments LN is here, and MN into the lengths shown. Okay, so that's just telling me to look at the 18, the 16, the 24, and the 27. Determine whether the side PQ and LM are parallel. Okay, let's do the converse up here. So I'm going to double check. I'm going to double check something like this. Since I am given all 4 numbers, do they create a proportion? So let's test it. All right, so I want to see, let me kind of color code. If I put LP over PN, so if I do 18 over 16, is that proportional to MQ over QN? Is that equal to 27 over 24? Okay, so question mark. So I could reduce these fractions down, okay? Another way to do it is I can really just cross multiply. And if I get the same number on both sides, I'm good to go. So if is 16 times 27, is that equal to 18 times 24? So 16 times 27 is 432. 18 times 24 is 432. So that means, yes, they are parallel. Another way to do this is we could just reduce these fractions down. So if I take 18 over 16 and I reduce it down, I get 9/8. Okay, do I get the same thing? So let me back up here. So if I take 18 over 16 and reduce it down, I can just divide both numbers by 2. I get 9/8. Do I get 9/8 when I reduce that down? So I can divide by what? 3. 27 divided by 3 is 9. 24 divided by 3 is 8. Okay, that's another way to do this. All right, so determine whether they're parallel. I'm going to say here, yes, PQ is parallel to LM by, let me go back to the name, let's quote it, converse of the triangle proportionality theorem. By converse of the triangle proportionality, that's quite a word, proportionality theorem. Okay. All right, so this is more of a checking type of theorem rather than, solving for x. All right, I'm going to create a second video for the next 2 theorems. So when you're done